The universe as a whole is extremely difficult to comprehend. It's much larger than we can imagine, with hundreds of billions of galaxies within it. Despite all the milestones achieved in space exploration for decades, we are still far from having deciphered all the mysteries of the cosmos. This is due in no small part to the fact that there may be galaxies and formations in space that simply elude our earthly gaze. The mysterious structures could lie outside the boundaries of the universe, holding terrifying secrets that can shatter our perception of the cosmos. And now, thanks to ever more advanced technology, we finally may have found one of these in our own universe. Join us as we dig deep into the bizarre structures found near the edge of the universe that could simply blow your mind. Thank you. To begin with, we know two crucial facts. The first is that the universe began just shy of 14 billion years ago in a singular event called the Big Bang. The second is that ordinary visible light has a finite speed. It travels at the amazing rate of 300,000 kilometers per second or 186,000 miles per second, or fast enough to circle the Earth about 7 times in a single second. We call the distance light can travel in a year a light year, which is equivalent to about 10 trillion kilometers or 6 trillion miles. Another important idea we need to understand is the difference between the visible universe versus the entire universe. The first is what we can see, and the other is everything. This isn't so hard to understand. Someone standing at the roof of the tallest building on the planet, the Burj Khalifa in Dubai, can see in every direction for about 100 kilometers or 60 miles. However, the surface of the Earth is much bigger than that, and the curvature of the planet makes it impossible to see everything. With the universe, the limiting factor is different, it's the speed of light. If our universe were static and unchanging, which isn't true, the farthest thing we could see would be 14 billion light-years away. That's because an object that far away emitted light the moment the universe began, and that light would just now be arriving at Earth. Light emitted from an object located 15 billion light-years away wouldn't arrive here at Earth for another billion years, so we couldn't have seen it yet. In our hypothetical static universe, the visible universe would be a sphere surrounding the Earth with a radius of 14 billion light-years. The entire universe might be bigger than that, but we would have no way of knowing since light from far distant locations hasn't arrived yet. But the universe isn't static, and that complicates things. The universe began in the Big Bang, and that bang caused the universe to expand. As it travels, light has to fight against that expansion, which takes it longer to get to you. To understand this, suppose a child stands 10 meters away from you and rolls a ball towards you at 2 meters per second. It will take 5 seconds for the ball to get to you. Now, suppose we have the same situation where you are standing on firm ground, but the child is on one of those moving walkways you find in airports. Suppose further that the walkway is moving away from you at 1 meter per second. Because of the motion of the walkway, the ball will not take 5 seconds to get to you, it will take 10. Alas, it gets more complicated. While the child was 10 meters away from you when they rolled the ball, because of the motion of the walkway, the child will be 20 meters away from you when the ball gets to you. The same thing has happened to the visible light from the Big Bang. That light traveled for 14 billion years to arrive at Earth. Now, and just like the child on the moving walkway, the current location of whatever emitted that earliest light isn't 14 billion light-years away, it's now 46 billion light-years away. We see the light from where it was emitted, not where the emission source is now. In this way, astronomers can say with confidence that the visible universe, which is the sphere around the Earth out to the distance of the oldest thing we can see, is 92 billion light-years in diameter, that is edge to edge. But that is merely the visible universe. What about the entire universe? How can we know about parts that are so far away that we have not even seen yet? Well, that's where things get really interesting. Since we can only see things when the light they emit or reflect reaches us, we can never see farther than the farthest distance light can travel in the time the universe has existed. That means the observable universe keeps getting brighter, but it is finite. The amount is sometimes referred to as the Hubble volume, after the telescope that has given us our most distant views of the universe. We'll never be able to see beyond that boundary, so for all intents and purposes, it's the only universe we'll ever interact with. But we know with some certainty that there's more universe out there, beyond that boundary. Astronomers think space might be infinite, with stuff, energy, galaxies, etc., distributed pretty much the same as it is in the observable universe. If it is, that has some seriously weird implications for what lies out there beyond the Hubble volume. You won't just find more different planets, you will eventually find every possible thing. If you go far enough, you'll find another solar system with an Earth identical in every way except that you had cereal for breakfast this morning instead of eggs, and another where you skipped breakfast, and one where you got up early and robbed a bank. In fact, cosmologists think that if you go far enough, you will find another Hubble volume that is perfectly identical to ours. There's another version of you out there mirroring your every action 10 to the 10 to the 188th meters away. That may seem unlikely, but then infinity is awfully infinite. Indeed, in 2008, astronomers discovered something very strange and unexpected. Galactic clusters were all streaming in the same direction at immense speed, over 2 million miles per hour. New observations in 2010 confirmed this phenomenon known as the dark flow. The movement defies all predictions about the distribution of mass throughout the universe after the Big Bang. One possible cause, massive structures outside the Hubble volume exerting gravitational influence. This would mean that the structure of the infinite universe beyond our view is not uniform. As for the structures themselves, they could be literally anything, from aggregations of matter and energy on scales we can barely imagine to bizarre warps funneling gravitational forces from other universes. The story doesn't stop there. In 2021, British PhD student Alexia Lopez was analyzing the light coming from distant quasars when she made a startling discovery, challenging our very understanding of the universe. Specifically, she detected a giant, almost symmetrical arc of galaxies 9.3 billion light-years away in the constellation of Boötes, the herdsman, spanning a mass of 3.3 billion light-years across. The structure is a whopping 1/15th the radius of the observable universe. If we could see it from Earth, it would be the size of 35 full moons displayed across the sky, known as the giant arc. The structure throws into question some of the basic assumptions about the universe. According to the Standard Model of Cosmology, the theory on which our understanding of the universe is based, matter should be more or less evenly distributed across space. When scientists view the universe on very large scales, there should be no noticeable irregularities, everything should look the same in every direction. Yet the giant arc isn't the only example of its kind. These gargantuan structures are now forcing scientists to reassess their theory of how the universe evolved. Lopez was studying for her master's degree at the University of Central Lancashire in the United Kingdom when her supervisor suggested using a new method to analyze large-scale structures in the universe. She used quasars, distant galaxies that emit an extraordinary amount of light, to look for signs of ionized magnesium, a sure sign of gas clouds surrounding a galaxy. When the light passes through the ionized magnesium, certain frequencies are absorbed, leaving unique light signatures astronomers can detect. As Lopez says, I looked into the known and documented galaxy clusters and then started plotting what these areas look like in the magnesium-2 method. One cluster I looked at was very small, but when I plotted it in magnesium-2, there was this interesting dense band of magnesium absorption across the field of view. This is how I ended up discovering it. It was a happy accident, and I was just lucky that it was me that found it. What Lopez's happy accident uncovered was simply astonishing. When looking towards the constellation Boötes, a cluster of between 45 to 50 gas clouds, each associated with at least one galaxy, seemed to arrange themselves in an arc 3.3 billion light-years across. That is a considerable size, given the observable universe is 94 billion light-years wide. According to Lopez's article, it is extremely unlikely, a probability of just 0.0003%, that such a large structure could have arisen by chance. It suggests that it may have formed due to something in the natural physics of the universe that we currently don't account for. Her findings directly challenge a central facet of the standard cosmological model, the best explanation we have for how the universe started and evolved. This facet, known as the cosmological principle, states that on a large scale, the universe should look roughly the same everywhere, no matter your position or direction in which you are looking. There should be no giant structures, rather, space should be smooth and uniform. This is convenient as it lets researchers draw conclusions about the whole universe based only on what we see from our corner of it. However, it also makes sense. Following the Big Bang, the universe expanded outwards, flinging matter in every direction simultaneously. There's another problem. According to the Standard Model, structures like the giant arc simply wouldn't have had time to form. The current idea for how structures formed in the universe is through a process known as gravitational instability, says Subir Sarkar, a professor of theoretical physics at the University of Oxford. About 1 million years after the Big Bang, when the universe was expanding, tiny fluctuations in density led to bits of matter clumping together. Over billions of years, the pull of gravity eventually led these clumps to form stars and galaxies. However, there is a size limit to this process. Anything larger than about 1.2 billion light-years across simply wouldn't have had sufficient time to form. To form structures, you need particles to congregate close to each other so gravitational collapse can occur, says Sarkar. Those particles would have to move in from outside the structure to get there. So if your structure is 500 million light-years across, light would take 500 million years to move from one end to the other. However, the particles we are talking about are moving much, much more slowly than that, so it would take billions of years to create a structure of this size, and the universe has only been around for about 14 billion years. The giant arc, discovered by Lopez, isn't the only large-scale structure discovered by astronomers. There's the Great Wall, also called the CFA2 Great Wall of Galaxies, discovered in 1989 by Margaret Geller and John Huckra. The wall is approximately 500 million light-years long, 300 million light-years wide, and 15 million light-years thick. Even bigger is the Sloan Great Wall, a cosmic structure formed by a giant wall of galaxies, discovered in 2003 by J. Richard Gott III and Mario Jurek and their colleagues at Princeton University. That wall is nearly 1.5 billion light-years in length. In the last decade, the discovery of these behemoths has accelerated even further. In 2014, scientists discovered the Laniakea supercluster, a collection of galaxies in which our own Milky Way resides. Laniakea is 520 million light-years across and contains roughly the mass of 100 million billion suns. Then, in 2016, the Boss Great Wall, a complex of galaxies over 1 billion light-years across, was uncovered. Boss is made up of 830 separate galaxies that gravity has pulled into 4 superclusters. The galaxies are connected by long filaments of hot gas. In 2020, the South Pole Wall, which stretches 1.4 billion light-years across, was also added to the list. However, the current record holder for the biggest of these structures is the Hercules Corona Borealis Great Wall, discovered in 2013. It spans 10 billion light-years, more than 1/10 the size of the visible universe. We calculated it, and then realized, oh, this is the biggest thing in the universe, says John Hakila, professor of physics and astronomy at the University of Alabama in Huntsville. Their concern was justified. Both Hakila and Lopez performed a range of statistical tests to try to prove that the results couldn't be down to chance. For the giant arc, the results have a confidence level of 99.9997. In scientific research, the gold standard for statistical significance is known as 5 sigma, which equates to a probability of about 1 in 3.5 million that the results are down to chance. The giant arc reached a significance of 4.5 sigma, so there's still a possibility that the structure is a chance arrangement of stars. Our eyes are very good at seeing patterns. You might see initials in the clouds, but that's not a real structure. Your mind is imposing a structure on what is actually random, explains Sarkar. However, I don't think that is the case in this situation. I think it is a genuinely physical chain of superclusters, he says. If more structures like the giant arc and the Hercules Corona Borealis Great Wall are proven to exist, astronomers will be forced to rewrite, or at least revise, the Standard Model of cosmology. It isn't the first time that the model will have had to have been adapted. In 1933, Caltech scientist Fritz Zwicky measured the mass of a cluster of galaxies and found the number to be smaller than he expected. The mass was so small, in fact, that the galaxies should have flown apart and escaped the gravitational pull of the cluster. Something else, therefore, must hold the clusters of galaxies together, he figured. This something is dark matter, a mysterious substance thought to make up 27% of the universe. Then, in 1998, the model was further adapted to include dark energy after two independent teams of astronomers measured the expansion of the universe and found that it was actually speeding up. Either way, we should know for sure within the next few years, as advanced technologies may provide astronomers with an unprecedented view of the universe. This is in part why infrared telescopes, such as NASA's newest flagship mission, the James Webb Space Telescope, are so crucial to understanding the early universe. There's an edge to where we can see it in the wavelengths we're familiar with. At distances of 31 billion light-years, corresponding to a time of just 550 million years after the Big Bang, we reached the edge of what we call reionization, where the majority of the universe is mostly transparent to optical light. Reionization is a gradual process that takes place unevenly. It's like a jagged, porous wall in a lot of ways. Some places see this reionization happen earlier, which is how Hubble spotted its most distant galaxy ever at 32 billion light-years away, just 407 million years after the Big Bang. But other regions remain partially neutral until nearly a billion years have passed. JWST has now taken us even farther, showing us galaxies as far back as 330 million years after the Big Bang, where they still appear large, evolved, and are not quite pristine in terms of the elements that are present within them. There must still be stars and galaxies out there, beyond even what JWST has shown us so far. Beyond those limits of what our current telescopes can see, we can still measure the indirect signs that stars have formed through the emission of light from hydrogen atoms themselves, which only occurs when stars form. Ionization occurs, and then the free electrons recombine with the ionized nuclei, emitting light in the aftermath of that. Right now, we only have the indirect signatures of this signature of early star formation, although there are many that dispute the validity of this signal, indicating that young galaxies existed as early as 180 to 260 million years after the Big Bang. These proto-galaxies formed enough stars that we can see the first hints of their existence buried in the data, corresponding to a distance of between 34 and 36 billion light-years away. Although our current telescopes haven't seen these galaxies directly, the great expectation of many astronomers is that a long enough deep field exposure with JWST will reveal them. However, noting that although we can look as far away as our telescopes can take us, there will always be a fundamental limit, even if space itself is infinite. The amount of time that passes since the hot Big Bang is not. No matter how long we wait, there will always be an edge that we will never be able to see past. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.